Hello everybody, it's really great to be with you today. Let me thank the organizers for inviting me here. I will change gears a little bit from the talks that we heard already today, and I will talk about some of the latest updates on the Hubble tension that I'm sure that everybody heard already in this audience. At the beginning, I was thinking of giving a more theoretical talk about the models that can explain the H0 tensions and the reasons why many of these models do not really work yet to solve this. However, there have been a few updates in the summer about further checks and maybe hints of his systematics in some of the measurements, and I thought that actually this is important to discuss. So the first part of this talk will be actually devoted to discussing some of these recent results. So the Hubble tension is essentially summarized in this plot that I modified from a paper last year with some of the latest measurements as well, where you have the measurement of the Hubble constant from the early universe on the left, in particular from the Planck CMB, that gives you 67.4 plus minus 0.5. And this value is also confirmed by the combination of BAO with BBN calculations and measurements of primordial elements that allow you to measure the density of baryons, and which also gives a perfectly consistent value with Planck, 67.6 plus minus 0.97 from the latest release of EBOS this summer. Now, what's common on these measurements, and these two measurements from the early universe, as you know, is the fact that they are not direct measurements of the expansion rate of the universe today, of course, but they can infer H0 only assuming a model, which is in this case the lambda CDM model. On the other hand, these measurements are very different from what is observed from more direct measurements, in particular the ones from supernovae that are calibrated with Cepheids. As you know, supernovae themselves can measure very well the relative distances between one supernovae and the other at different redshifts, but only if you can very accurately calibrate their absolute magnitude with some other probe of distances, you are able to infer the value of H0 from this data. And this is done in particular in the Shoes collaboration by using Cepheids that can calibrate the supernovae at, say, distances which are less than 50 megaparsec, and then Cepheids can determine distances through their period luminosity relation, which is calibrated locally, for example, in the Milky Way or in the Large Magellanic Cloud, or in a galaxy that contains a water megamaser. And all these different systems have geometric ways of determining distances and therefore calibrate the Cepheid relation. Now, this value has also been, so this value is extremely, is really little model dependent, and was also confirmed by time delays of multiply imaged quasars, which measure the difference in the arrival of, in time arrivals of different images that are strongly lensed. So from quasars, and this value also is high, confirming with error bars that are fairly small the measurements from supernovae and Cepheids. And so if you combine the two, as it was done in this paper last year, then you have a more than 5 sigma discrepancy with the CMB data. I just want to mention that there are many more measurements of H0, in particular, for example, the one combining 6 different water megamasers from Pesce et al. From this year that also gives a high H0 values. And However, these other methods give fairly larger error bars, and so clearly the tensions is not that strong if you take into account these other measurements, and notably, for example, the one from gravitational waves. Now, something very relevant that happened, and clearly, let me add, clearly the whole interest of the community for this tension is the fact that if we are able to discriminate or to eliminate the hypothesis that this tension is due to systematics in these measurements, then clearly we can focus on trying to find theoretical models that can change the lambda CDM model and therefore change the inference from Planck and BAO of H0. And also let me mention that there is also a new measurement from supernovae, which now calibrates the supernova not with Cepheids, but with the tip of the red giants from Friedman et al. They find a somewhat value which is a little bit, say, in between the CMB and the Hughes measurement, with an error bar, however, that makes it compatible with both. So this certainly, this alternative way of calibrating the Cepheids will be extremely important to either confirm or not the difference that we see in these measurements. Now, one very important, I would say, or very interesting result that came out this summer is the one from the Atacama Cosmology Telescope, which is a high resolution polarization CMB experiment that is at its fourth data release. And the results that they published are from 3 years of data in 2 frequency channels observing about 6,000 square degrees of the sky. They show that their constraining power is now comparable to what was from WMAP, and it's about a third of what Planck could do. And we got very excited for these results. This was a great achievement from ACT. It's fantastic that actually they performed these analyses mostly blind, although they were forced to do a few small corrections to their data after the blinding to solve some internal inconsistencies. But overall, ACT finds a value of H0, which is in perfect agreement with Planck, again, with an error bar which is about 3 times the one from Planck, and then combined with WMAP, the error bar is about a couple of sigma, a factor of 2, about 2 larger than Planck. Now, this is fantastic. They discuss the fact that their consistency of their whole parameter set of lambda CDM parameters is in agreement with Planck at the 2.7 sigma level, 2.3 sigma in WMAP, and this is essentially due to the fact that they find values of NS and omega baryon which are discrepant from Planck. Now, whether this is a statistical fluctuation or whether this is a sign of residual systematics, only they have already a lot of more data in the can, and I'm sure that further analysis will be able to solve and to robustify this analysis, also solving this possible curious difference. Now, there is a second paper that I would like to discuss, a second result, which is from George Statu this summer, pointing out that there might be a discrepancy from one of the anchors in the first rung of the distance ladder from Hughes. The anchor is simply one of the geometrical ways that are used to calibrate the period luminosity relation of Cepheids. And in particular, so this is a rather technical argument. I will not go into the details, but I'm happy to answer questions about this, is essentially the fact that if you measure the distance to, in particular, this galaxy NGC 4258, which contains a water megamaser, and that allows you to to measure the distance of this galaxy directly in a geometrical way, and then you compare with what you can do with Cepheids contained in this galaxy and calibrated with the Cepheids that are contained in the Milky Way or the Large Magellanic Cloud, then there is a 2 to 3 sigma discrepancy between these two distances, which might point towards a possible residual systematics in this measurement in particular. And clearly this would affect and would have an impact on the inferred value of H naught. The very cool thing about this paper is that there are also, they also now contain also the answers from the SHOES team. And so you can see the different points that Stadio makes and the different answers from the SHOES collaboration, which also was interested in this result and will make further checks in order to better understand whether this discrepancy is systematic or just a statistical fluctuation. And then finally, I want to point out this result from Birrer et al. About the time delays of multiply imaged quasars. So as I said, I mean, this method relies on measuring the difference in the arrival time of quasars, which are variables and have features. And so by observing the spectra of these quasars for a long time and the different images of the same spectra, you can calculate the difference in time of the arrivals of these photons. And this depends on a combination of the distance to the lens, to the source, and the relative distance, and which themselves depend on H naught. However, in order to infer these distances, you need to have a knowledge of the lens reconstruction. And sorry, the lens reconstruction. I meant the lensing potential of the lens. And there is a problem with this because from lensing data alone, you cannot unambiguously reconstruct this potential. There is a degeneracy, which is called the mass sheet degeneracy, which essentially tells you that there is a degeneracy between the source position and the potential profile of the deflector. Now, the way people have used to break this degeneracy is to assume a particular lensing profile. For example, the baseline values that are used here used profiles which might be, for example, a power law or a Navarro-Franco-White combined with stars. But several different papers and now also Birrer point out that if you relax this assumption, your constraints on H naught from quasars relax by about a factor of 4. Then you can use other data to constrain this lens profile, for example, stellar kinematics data, which are, however, not constraining enough to really recover the constraining power that you have when you fix the lens profile. And you can also use data from other systems that allow you to constrain the population of the stellar kinematics and therefore of the lens potential of these systems, and they show that the error bars are still very large, and you can actually move the central value of H naught by a very consistent amount. So I think this was a very interesting paper that was received a lot of attention from the community because there are, for example, some models that try to solve the H naught tension by working with the physics of Cepheids and supernovae. And one strong reason to say, you know, you cannot solve the H naught tension just working on modifying the constraint from supernovae and Cepheids, because you have this other constraint that is in agreement. And so if we start saying that this constraint now is not as strong as we might think, then this could put back on the table a few models that were actually proposed to solve the tension. So this is all to say that we are still really in the phase of having more data, trying to robustify these findings and try to convince ourselves that this discrepancy is actually there. And as I was saying, the exciting part is if we are able to indeed confirm this, then we might be pushed to find new models to actually try to explain this difference. And this plot summarizes a little bit what you can actually do, some of the main ways people have thought to solve this. I would like to mention this very nice paper from Lloyd Knox and Marius Milea last year that tried to have a review of the different classes of models that have been proposed. But essentially, the idea is the following. So the CMB as well as BAO measure the angular scale of the sound horizon. And what we are interested in is to infer distances from the CMB and BAO, from which we are then able to infer H naught. Now, if you measure an angular scale, then in order to know the distance, you need to know the physical dimension of this angle, which in this case is the physical dimension of the sound horizon. The CMB is able to measure these or to infer this quantity, assuming a model, assuming, for example, the lambda ACDM model, under which, I mean, this quantity is just the integral from the beginning of time, say, till the coupling of the sound speed divided by the expansion rate of the universe until the coupling. And so the CMB gives you this RS, and then once you have RS and theta, you can infer the distance to the last capturing surface for the CMB or for BAO at the redshift where you have the BAO measurement. And then your work clearly is not done yet, because then the distance depends on the integral from today till the redshift of the measurement of the inverse of the expansion rate of the universe, which is then now dependent on H naught and other parameters such as omega matter and anything else that can impact the expansion rate at late times. So there are different ways of acting in these different parts. And clearly the first, probably the most evident thing is that you say, okay, but the CMB only really constrains the distance to the last capturing surface, and it's not sensitive to really, or it's a little sensitive to the details of what the expansion history did at later times. And so one way of solve the Hubble tension is to do something, you know, to have, for example, a more free evolution of dark energy compared to a simple cosmological constant. And so many people have explored this possibility of having some late time dynamics of dark energy, dark matter, dark energy interactions, dark matter decaying, modified gravity, and so on and so forth. And the main problem with this kind of solution, so that allows you to change the mapping from the distance to H naught, is the fact that we have a lot of data at late redshifts, BAO and supernovae, that actually constrain the evolution of H of Z in a very fine way. And this is actually shown in these plots. There are many different authors that made this point. We have actually supernovae data and BAO covering from redshift essentially of 0.01 until redshift of 2. And if you don't calibrate the BAO, so you don't know the RD, RS, the physical dimension of the sound horizon, and for the supernovae, if you don't know the absolute magnitude, and so from the single ones you cannot constrain H naught, they still constrain the relative distances. And so they still constrain the evolution with redshift of h of z. And their evolution tells you that dark energy didn't do something wildly strange in this range of redshift. And so we have data between 0.01 and 2, and then below 0.01, you have the calibration of the supernovae in galaxies that also contain Cepheids and that are calibrated today. And you need these distances to agree with each other. So until you have these Cepheids and supernovae, by definition, you need to have a calibration which agrees with the local universe and which wants potentially an H naught, which is 74. So how to relate this is very, very hard. And if you essentially try these ways of reconstructing H of Z, even in a phenomenological way with very fine binning, it's very hard to reconcile the early universe and late time universe measurements with these solutions because of this very accurate sampling of the and measurements of the expansion history of the universe. So for these reasons, people have more focused on early time solutions, and there are many different, and I don't have the time to go in the details of all of them, but I will mention that many of these solutions, not all of them, focus on the fact that you can change the model that describes how to calculate the physical dimension of the sound horizon. It was calculated that, so with Planck, you have a constraint on this measurement, which is about 147 megaparsecs. Sorry, there are no units on the slides. 147 megaparsec is in particular the sounder horizon at parent drag. And the needed RS in order for the CMB to give you a measurement of H naught which is compatible with local measurements requires an RS which is rather 138 megaparsecs. And since the CMB actually determines this value with extremely good accuracy, this is many sigma away from what is measured. So you need a model that allows you to decrease RS more around these values. There are different ways you can do this. If you look at this relation here, clearly you can play with changing the time of when the coupling happens in the CMB. You can change, for example, by changing the way recombination evolves. You can change the sound speed by changing the properties of how, for example, dark matter and or baryons interact. Or you can change the expansion history at early times, for example, with an extra number of relativistic species or early dark energy models. And, or a very different idea, actually this angular scale of the sound horizon is not completely a direct measurement from the CMB, because you also have a phase shift which depends on free streaming neutrinos. So the idea is that if you don't have free streaming new neutrinos, for example, because they strongly interact, then you can change the inference of theta and therefore the inference of H naught. No one of these models really change the tension when combining all the available data sets. So more in detail, the idea of changing H of Z. So this, as the dark energy, this was the other possibility that was immediately tried in the Planck collaboration, of which I was part of, and also from the community. So the idea that you just add a relativistic component that increase the radiation density in the early universe, and that can therefore increase H of Z here, and therefore decrease RS. And the problem with that is that, however, changing the expansion history at early times also changes the scale of the damping tail in the CMB. And this very tightly constrains NF from CMB measurements. This is why essentially Planck puts a very tight constraint on NF with very close to the standard value of 3.046. And also H naught, although clearly there is a degeneracy between NF and H naught, which increases the error bar from 0.5 to 1.4. I don't know why. Can you see these lines? I don't know why my computer is doing this. Okay.
Some kind of bombing going on.
Okay.
So we need to see if I can.
What, sorry?
No, you can continue. I think someone is.
It's
been gone. It's gone.
Sure. Still, you get a low H naught from the CMB data, and so in order to avoid these constraints from the damping tail, some more elaborate ideas have been proposed. For example, early dark energy that had a lot of momentum, and a lot of different authors actually worked on this kind of model, proposing different variations. And the idea here is that you have a scalar field essentially that starts rolling at a critical redshift, which is around the epoch of matter and radiation equality, and which allows you to basically change the expansion history of the universe in a redshift range that impacts more strongly the sound horizon compared to what it does for the scale of the damping tail. Essentially, the damping tail, what you can see from this plot from Knox and Milea, the contribution of the dimension of the damping scale essentially gets contributions around the epoch of recombination at redshift 1000, while the sound horizon gets contributions also from earlier times. And so if you have a component such as early dark energy that changes the expansion history earlier in times, and then less when the damping scale becomes or gets its contributions in its dimension, then you can accommodate a larger or or you can solve a little bit better detention compared to the NF model. However, it was pointed out, again, from many different authors, even the ones that worked on this model, and more recently by Hill et al., is that early dark energy do not agree with the latest results from weak lensing experiments, such as DES or KIDS or HAC, because it increases the value of sigma 8, so increases the discrepancy or the gravity of the other tension that excites the CMB community, which is the sigma 8, the difference in the amplitude of the matter perturbations today as measured by the CMB and weak lensing measurements. So this, adding this data set also puts the early dark energy models in difficulty. And also there is this problem of fine-tuning of the parameters of the models in order for it to actually work for the H-naught tension. Now I see that my time is almost over, so I will be a little bit quicker for the few next slides. I wanted to mention that the other possibility is changing the way recombination happens, and essentially because in this way also you change the time over which you do your integral for the sound horizon, the physical dimension of the sound horizon. However, the problem with this, and there are different physical models that can do this, the mass of the change in the variation of the fundamental constants. There is one solution that proposed the change in temperature of recombination. And the idea is just that if you change just very easily the time at which recombination happens. So basically the distance to the last scattering surface, in order to keep the angular scale that we measure very well from the CMB, you also need to change the distance to the last scattering surface and therefore H naught. So there is a degeneracy between recombination and H naught. But the problem is that all these solutions are highly constrained by the BAO, because yes, you can change H naught at late times to adjust the distance, but then you have the BAOs that actually sample the distance much closer to us. And so if you just change H naught, you will actually change the angles that are measured by BAO in a way which are incompatible with what we actually observe. So these solutions are highly constrained by BAO. And last but not least, people have also looked at interactions between different species in the early universe to try to solve this tension. I just want to mention the neutrino-strong interactions between neutrinos. So these are self-interacting neutrinos, and as I was saying, this basically changes the inference of theta s from the CMB, because it eliminates the phase included or in the CMB peaks positioning due to the free streaming of neutrinos. The problem with this is that the interactions would be so large that are probably ruled out by current laboratory constraints. And so I will just finish just by saying that
I'm being told by Sriram that you could be a bit relaxed because we haven't been able to get the other speaker of the session. So
okay.
Take it easy.
Anyway, I finished. I just wanted to mention the fact that the future is bright. Clearly, I am a CMB person and I advertise the CMB, but this is true for basically all of the probes that I talked about today in this talk. And there are current ground measurements from SPT and ACT that will improve our knowledge on the high resolution polarization, and many of the models that I talked about have distinctive signature. For example, here showing a plot from Smith et al. Sorry, I forgot the reference, showing how essentially the early dark energy models will be constrained by future experiments such as CMB S4. And even in the vanilla lambda CDM case, an experiment such as SPT3G, but there are similar considerations for advanced ACT or Simon's Observatory, will be able actually to improve, for example, in lambda CDM, our knowledge of H naught by a factor of 2 when combined with Planck, and as I said, improve also the knowledge on all the extended models that I talked about. And with this, I really thank you for your attention.
Thanks, Sylvia. Am I audible? Yeah. So thank you very much, Sylvia. This is a very nice tour of the latest developments in the so-called H naught tension. I think it's particularly nice for me to see the latest results again. So let's get to the questions right away, because Sandeep Trivedi is unable to join us now, so we will have the discussion session right away. So let's take the questions that have come in the chat box. So I think there's a question from Bikash about why early universe and late universe predictions of Hubble parameter is different.
I'm not sure I understand what he means. I mean, the early universe measurements that I showed in the first slide are indirect. So they are based on a model. If you change the model, you change these values. The CMB is measuring apart from the CMB lensing and integrated Saxe-Wolf, but essentially it's measuring what's happening at redshift of 1100. And it has sensitivity to whatever else just because it's sensitive to the distance to the last scattering surface, but it's not really sensitive to what's happening locally, and especially not in the detail of how the universe is expanding today, apart from the integral measurement until the last scattering surface. And the supernovae and Cepheids, on the other hand, are measurements that are done very locally. I mean, these are supernovae from 0.01 to, I think, 0.2. So it's not even all the way to 2 as the Pantheon sample that are rather used to constrain the evolution of dark energy and so on and so forth. So, and these are less model dependent. So simply if you allow more larger possibility for dark energy models evolving and so on, I mean, your measurements are so localized in redshift that these do not change the value of H0 from these measurements. And this was recently also rechecked by Dawan et al. In a recent very nice paper.
Thanks, Sylvia. Vikash, does that answer your question? I'm unable to unmute you so that you can ask your question properly. If this answers your question, then we can move to another one, which sort of can't find right away, but it was if the discrepancy between, this is from Joseph Jackson, discrepancy between water maser and Cepheid measurements mentioned earlier is systematic, how much could it resolve the Hubble tension?
So it depends on where the systematic is, because, okay, so the technical point that George is making is that, so you have this distance, if you use this distance to the water megamaser, and if you use this to calibrate the Cepheids in this NGC 4258, you find actually a slope in the PL, in the period luminosity relation of the Cepheids, which is shallower than what you find in local environments. Local environments, I mean, in the Milky Way or in the Large Magellanic Cloud. And he says probably this is an observational bias due to the fact that in this galaxy, it is harder to observe fainter Cepheids, which might bias the slope. And so if you use the distance to NGC 58 from the megamaser, and if you use the slope of the CL relation that you observe in the Milky Way or in the LMC, which is steeper, then you can get only from this calibration of the supernovae and H0, which is 70 plus minus 1.8. However, the possibility is that the distance to the megamaser is wrong. I mean, there are other, I think other, I mean, there are 5 anchors that tell us that different anchors of the Cepheids and NGC 4258 is only one of them. And it's the only one that gives you such a low value of H0, with this additional caveat of you need to also impose a prior on the Cepheid PL relation. So if you don't believe any other anchor, you only believe this NGC and you believe the slope of the PL relation from the Cepheids from the Milky Way or LMC, then H0 could be as low as 70, but maybe for these, maybe it's the distance to NGC 4258, which is wrong, and then all the others are right, and then H0 is still high.
Thanks, Sylvia. This is a question from Swagat Mishra, who's a senior graduate student at IUCAA. Swagat, can you try to unmute yourself and ask the question, or I can read it out?
I'm able to do that. Yeah, great.
Okay, great. Yeah, I think people can do that. Yeah, great.
So, my question is, do any of these early dark energy models, do they really shift the Hubble value from 67.4 all the way towards 73?
No, you are not able to do 74 in any case with any of these models. you do maybe 72, and this is only, you know, not taking Planck alone data. I mean, you take Planck, you do early dark energy, you put the measurement from H naught, you fit the two data sets, and then you are able to shift a little bit the H naught to a value which is in less tension with Reese. So they don't do all the way.
How less? Like how much can you relax the tension? 2 sigma, 1 sigma?
So it's hard to quantify this, because the way it was quantified in papers that were published about this were quantifying the difference in the Hubble constant from comparing the shoes measurement with the one that you get from Planck plus shoes in the early dark energy models. And if you do so, I think it's between 1 and 2 sigma. The problem with that is that the way usually we quantify this is by taking, for example, the Planck alone constraint on H naught and Hubble, and then compare the two. The problem with that is that Planck alone data from these models have extremely non-Gaussian distributions, and it's fairly hard to sample this space. So how exactly to quantify this in this simple how many sigma, it's not completely trivial.
And the second thing is, if I think correctly, you need, for early dark energy, you need about 10% of them at some redshift of 3 or 4.
Mm-hmm.
So if you're freezing a scalar field, if it's a slightly higher value of phi, then you're going to get accelerated expansion right away, right?
Absolutely, and this is the fine-tuning problem of these models. I think it's unsolved. I think I saw some papers that are trying to find, you know, like more natural ways of having such an early dark energy mechanism with such a fine-tuned value. But yes, it's one of the limitations of this model.
Thanks a lot.
Okay, there's a question from Shahnawaz. What can be the theoretical motivations for early dark energy cosmology? I mean, how do these scalar fields arise?
Yeah,
you
I
can
think
also unmute yourself if you wanted to talk.
Yeah, I think this is still an open question, also because the potentials that are currently used are quite, I think there is not a strong theoretical motivation to use the particular potential shape that they use. I think this is still a matter of discussion, whether these models are, you know, viable from a theoretical point of view. I mean, I think this was it was discussed in detail in the paper from Smith et al. 2019, which gives some more theoretical background for these models. Yeah, I can also only refer to that reference for more details.
Okay, thanks, Sylvia. Devaprasad Maiti, is it possible to elaborate on the connection between H0 tension and primordial magnetic field? Yeah,
this is a very nice model that was elaborated by Levon Pugasian and Carsten Jadamsi. And the idea here is that at small scales, primordial magnetic field can produce clumping that increases locally the density of baryons. And in this way, you change recombination, because recombination processes goes as the square of the baryon density, while reionization goes linearly with the number density of baryons. And so if you can locally cluster and form these clumps of baryons, for example, due to the presence of primordial magnetic field, you are able to change the story of recombination, and so to relax essentially the constraints that you get from the CMB of H0. So many of these models, I mean, almost all of these models just increase error bars. Huh? I mean, the value of H naught from Planck from most of these models is around 67, maybe shifts to 68, but it's always in the low ballpark, and you increase the error bars. And also for this case, when you add, so you open up this degeneracy between H naught and in this case is the clamping factor for primordial magnetic fields. And again, if you add BAOs that sample the expansion history at lower redshifts, the evidence for these models decreases.
Great, thanks, Sylvia. Aritra Kundu is asking whether you can say a bit more about the relationship between dark matter baryon interaction and the
so the idea is, so I think these models do not work. They are highly constrained by the CMB. The idea is, in general, you might think that you might change the way the sound speed evolves. And this depends on basically the ratio of baryons and the photons. If you add, for baryons, if they have additional interactions, they might change the overall sound speed of the photobaryonic fluid, and therefore change your inference of RS. But the problem is that this has other signatures. For example, baryons are responsible for the odd-even amplitude of the CMB peaks, the depth of the potentials, and so they change the amplitude of compressions and expansions in the early universe. And if you have further interactions, you would change also this alternation of the amplitudes of odd and even peaks. So essentially, you would have other signatures that I think strongly constrains these models as well.
Thanks, Sylvia. There's a question by Rajgopalan Nair. I don't quite understand the question. Would you like to unmute yourself and ask it?
Hello, good afternoon, everybody. My question comes because of the Friedman's equation. 2h square is proportional to density, sum over the density of components in the universe. This is applicable to FLRW universe, and the universe is flat. So my question is, because I don't know if in the early universe the space was essentially flat or not. So if h square depends on parameters other than density, for instance, here the curvature of the universe as well, which may not be zero in the early universe, will one be able to know it? So that is the question.
But what do you mean that the curvature of the universe is non-flat in the early universe and then is flat now? I mean, how do you do that? I'm not sure I understand.
If the density is,
are you asking whether there are constraints on the curvature of the universe that do not depend on the late universe, but only from the early universe?
Will not the curvature be affected by the density of the components? In the early universe, the density was huge.
Yes, but the curvature at very early universe, in the very early universe, I mean, compatible with current constraints, I mean, is you're essentially sensitive only to the radiation density and to the matter density in the very early universe.
No, Rajgopalan, maybe I should just interrupt. I mean, it's a well-known fact in basic cosmology that the curvature density tends not to dominate at early times. You know, if you look at how it falls off with expansion of the universe, it falls off slower than matter density and radiation density, hence only tends to dominate now. Or if it dominated in the past, it would dominate even more now. And we see it to be almost zero now. So in the framework that we are working, it's very unlikely to imagine a situation where the curvature is flat now and the curvature was non-flat in the early universe. Okay.
Okay.
Thank you. And let me now go to
There
some
were,
hands up.
Tarun, there are two
Chandrasekhar had a
questions.
question. Sorry, Chandrasekhar.
Yeah, Chandrasekhar and Robert Brandenberger had questions.
Robert. Okay, yeah. Yeah, right. Chandrasekhar, do you want to unmute yourself or should I read out your question? How much of our knowledge of reconstructed lensing potential contributes or affects the measurement of H0 from Planck?
Nothing. I mean, for when you use temperature plus polarization, I think, if I remember correctly, if it was changing by very little. But you would take the measurement from the power spectra, and it would not change anything to this discussion. Then it's interesting because you can use then lensing to have independent CMB lensing to have independent constraints from the CMB spectra and also infer H0, for example, combining CMB lensing with PAO and BBN, and you also get a low value of H0. But itself, to the baseline value of H0 from Planck, it has a very small impact.
Okay. So let me go to Urjit Yagnik. Okay, before that, Joby has his hand up. Do you want to unmute yourself and ask the question?
Yes. Hi, can you hear me?
Yeah.
Okay. So you mentioned two different ways of measuring H0 from the supernovae by calibrating them with using the Cepheids. That was one. And the other one was, I don't remember that one, sorry.
The tip of the red giants.
The red giants, yeah. So what are the redshifts that are used for calibrating in both the cases?
So the Cepheids, so they are both, so the problem is essentially that you don't have these probes at very high redshift. So otherwise you would use, for example, Cepheids. If you were able to observe Cepheids well within the Hubble flow at redshift 1 or redshift 0.1, then you would directly use Cepheids to measure distances and therefore H0. So the problem is that they are only at lower redshift. Cepheids are below 50 megaparsec, so below 0.01, and I think the tip of the red giants must be the same. I mean, okay, I don't remember exactly at what megaparsecs are these. Well, no, I'm sorry, I said something stupid, so I know. You need, similarly to the Cepheids, the tip of the red giants, you need to calibrate it locally, for example, in the LMC. And then you need to observe the tip of the red giants in the second ladder. So essentially these close by supernovae that are hosted by galaxies that also contain Cepheids. Well, they also, in these same galaxies, you can also measure the tip of the red giants. And so it's basically the same redshifts.
Okay, so I was asking because one of the papers I went through, I came across this proposal that this tension could be because the part of the universe that we are living in is underdense, and because that's underdense, it affects the calibration of the supernovae. And if that's the case, so what are your comments on that?
I am prepared for this question. So clearly, one of the ideas were that we might be living in a giant void, and that this is the reason why the apparent value of H0 actually is high. It's just that we are not correctly correcting for the peculiar velocities induced by this giant void. This was tested over and over and again, this possibility, first from simulations that tells you that this void would need to be, I mean, the H0 value, the error bar contains the sample variance that includes the possibility that we live in a slightly overdense or slightly underdense region. And this sample variance contribution of the uncertainties was to the H0 uncertainty was estimated to be 0.3 kilometers per megaparsec. We need to solve from 67 to 74, and this accounts in lambda CDM only for 0.3 kilometers per second per megaparsec at 1 sigma. So this tells you already that if you believe lambda CDM, the void would rule out lambda CDM. Okay, we would need a gigantic void. The second problem with which, okay, we say, okay, we need to modify lambda CDM anyway, and so we have a giant void. The problem is that then you have all these supernovae that sample the expansion history very finely from redshift 0.01 to 2.26. And this was done with the Pantheon data, where they actually showed that you don't see, a change in the H0. You would need to see a change in the expansion rate at some point in the supernovae that, even without the absolute calibration, they tell you what is the H of Z, the relative H of Z at different redshifts, and they don't see actually a change that is compatible with such a large local underdensity.
Okay.
Sorry, who is the author for this paper? I would like to look it up.
Can you see my screen still?
I can see your screen, yeah.
Yes, all the references are here, but the latest, this work for supernovae is from Kenworthy et al.
Okay.
Okay, thanks.
Okay, thank you.
That's nice. Thanks, Joby. That was a good point. Urjit wanted to make a comment, or you also had a question? Urjit, please.
Since some people asked whether there can be any models that can give this kind of early condensation difference between the lambda CDM idea. Since there is a lot of talk of milli-charged particles, it is possible to consider a hidden electromagnetism. And we have considered a model like this, and then you can have fermions in the hidden sector condensing and creating some of the effects, although we have not studied all the detail of it. But so there are possibilities within basic physics that we can generate some deviations from standard lambda CDM.
Absolutely. I think, yeah, I don't remember the details of this model. I remember I've seen the papers. I'm not sure whether you can actually fit all of the data. I think that's valid for many of these models. But thanks for pointing this out, yes.
Thanks, Urjit. So Robert, do you want to unmute yourself, Robert? I don't think Robert is able
Okay.
to. Oh, okay,
So,
great, Robert, yes.
there was a paper about a year ago by Waffe and collaborators, Agarwal, Obiel, and Waffe, an effective interaction that dumps dark matter into dark energy. And that gave rise to a slightly larger value of H0. Do you have any comments on that?
But as far as I understand, these dark matter, dark energy interactions do not survive when you put all the data together. I mean, they do solve the H0, CMB, and the Hughes value, but as soon as you put BAO and supernovae, I mean.
No, I think this had BAO in it.
I don't remember the details of this particular.
I mean, it only managed to raise the value of H0 slightly to about 70.
Yes, no, this of course you can do. Yes, I mean, when I say they don't work, they can, it's not that BAO and supernovae put you back to 67. They can, maybe, you can resist to be at 70, but this is true for many of the models that I discussed.
But the nice feature of that model is that it was a natural mechanism.
Yes,
I
agree.
Yeah.
I agree, and I agree that there are ways of doing this. Some are nicer than others, and more natural and more physical, and I completely agree with you. My point is just that, I completely agree with you. When you add BAO and supernovae data, it's not that you go back to 67 plus minus 0.5. I mean, still you increase a little bit the error bars, you might shift a little bit the value, and then the detention is less prominent. And then you need to have, you know, two things that are happening. The CMB you need to extend the lambda CDM model, and you need the H naught value to have fluctuated particularly high from the shoes measurements at the level of 2 to 3 sigma instead of 4 or 5 sigma as it's in the current tension. And this is a little bit what we call, you know, it's a little bit having the blame to the two, giving the blame to both sides of the story and find a value of H naught, which is in the middle of them. That's a possibility, sure. Whether we call this a satisfactory solution, maybe, I'm not sure. Thanks for pointing this out, Robert.
Thanks, Robert. Did you want to comment further?
No, thanks a lot.
Okay, thanks, Robert. And I think that, oh, sorry, there's another question from Ranbir Sharma. What about non-parametric or model-independent methods to determine the Hubble constant?
Yeah, so model-independent, meaning you can reconstruct H of Z without having a model of dark energy model. Sure, it has been done, and it, you know, it has to respect the same constraints that I talked about so far. This has been done in many different ways. Raveri et al. Did it lately, you know, for EFT models that include all possible kinds of modified gravity models nicely, so on and so forth, in a very fine binning of redshift. But still, you have this problem that you fit the BAO and the supernovae, and they tell you that the only space for something happening is where you don't have data, which is below 0.01, essentially, in redshift. And then there, you cannot do much. I mean, then you are in the local universe with Cepheids and supernovae observing the same distances in a way. You would need dark energy to do something crazy in this very little range of redshift. So yeah, it has been done over and over again, and I think it's hard to solve the Hubble tension even with a model-independent way of reconstructing H of Z.
And thanks for the organizers for hosting this lovely meeting. Thank you very much.